In this question, we study a particle filter. Let's just zoom in for a second. We have 8 particles that land on this checkerboard. They're labeled A all the way to H. And some of them are on black squares, and some of them are on white squares. Given those particles, we'll assume that the probability of measuring black for any particle that falls in a black square is 0.7, and the probability of measuring white for any particle that falls in a white square is 0.6. From that, you can easily calculate the probability of measuring white if a particle falls in a black square, and the probability of black if the particle falls on a white square. Now I'd like to know what's the normalized importance weight after normalization of the particle labeled A if our measurement happens to be white. That's a number that you would like to put in over here. And I'm going to ask you the same question about the normalized importance weight of particle A if the measurement is black. To calculate this, you will go through these probabilities. For each particle, you will assign the measurement probability, and then you just normalize all of those so they add up to 1. In the first case, the answer is 0.2. And the way I got there is the probability of measuring white for A is 0.6, which is the number over here. But we have to normalize. And we find out that 2 particles get the white value, which is 1.2, 2 times 0.6. And all the other 6 particles have to get a non-normalized importance weight that is 0.3, which is 1 minus 0.7. So 6 times 0.3 is 1.8. So the normalizer in total will be 3. And 0.6 divided by 3 equals 0.2. In the second question, the answer is 0.08. Because we measured black, A gets a non-normalized importance weight of 0.4, which is 1 minus 0.6. There are 2 particles that get 0.4, which adds up to 0.8. And 6 particles that get 0.7, which adds up to 4.2. If we add this together, it's 0.4 divided by 5, which is 0.08. In this question, we assume that a particle A has a already normalized importance weight of 0.2. So there might be other particles, we don't even care how many, but their importance weights add up to 0.8. We now sample 3 new particles with replacement. What is the probability that this particle A is sampled at least once? And the way you derive this is by asking the question, what's the probability that particle A is never sampled? And then you take the complement of this. The probability that in any drawing A is not sampled is 0.8. Because we sampled it 3 times, we take 0.8 to the third. And that's the probability that A never occurs. So the probability that A occurs at least once is 1 minus that. And when you work it out, it's 0.488. This is a question about alpha-beta pruning in min-max search in games. Consider the following tree, where this is a max node and these are min nodes. We perform alpha-beta pruning. I'd like you to check all leaf nodes of these 9 leaf nodes over here in this tree that will be expanded, assuming that we expand from the left to the right, and we expand in depth first mode, of course, as always in these game trees. As we expand from left to the right, we go to the min node over here, and then we expand the first leaf, the second, and the third, and we pass back as the current min 4. As we now move into the second node over here, we first expand 5, which might be a larger max. But as we hit 2 and expand it, we realize that this node over here will have a min of 2 or smaller, and as a result, it can't contribute to the max anymore, so we cut it off, and we never expand 1. Finally, as we move to the right side, the moment we hit 1, we're done, because we know the max could be 4, but this branch over here will yield no value larger than 1. So we go back and never expand the nodes on the right side over here. These are 4 true or false questions for computer vision, and specifically projective projection. Consider a projective image of an object. Which of the following statements is true? If the object moves closer to the camera, the size of the projected image of the object will increase. This is true or false. Please just check one. If we use a camera with a longer focal length, as a result of using the longer focal length, the size of the projected image will increase. Check one. If we double the distance to the object, the projected image will be half as large as before. Check one. And finally, the ratio of the focal length over the distance to the object is the same as the projected size of the object in the camera plane. Please check true or false. And the answer is easily derived from the basic projection equation, here without the minus sign. So if we move the object closer to the camera, which means z decreases, then the size will increase. If z decreases, yes, the size will increase. If you use a camera with a longer focal length, then the size of the projector will increase. So if you increase f, then yes, x will increase as well in the same proportion. If we double the distance to the object, which means z is twice as large as before, the projective image will be half as large. And yes, if we divide by something that's twice as big, then the result will be half as large. And finally, the ratio of the focal length, f, over the distance to the object, z, is the same as the projected size of the object in the camera plane, x. This specific statement, we really forgot about the object size, uppercaps x, which plays a big role in this projective equation, therefore the statement is false. A question on stereo vision. An object at range of 100 meters leads to a 2 mm displacement for a stereo rig with focal length 40 millimeters. Now we double the baseline. What will happen to the new displacement that used to be 2 millimeters? What will it be now? The answer is 4, which is just twice as much as 2 millimeter. If we move our baseline apart, then the basic equation of stereo vision suggests that the displacement is proportional to the baseline, and therefore it decreases correspondingly. Here's a structure for motion type problem that is similar to what I asked you on a homework assignment. Assume that there's a world of 3-point features that will be named 1, 2, 3, but I won't tell you which one is which. There are 4 pinhole cameras, A, B, C, and D, and they all have a left, center, and right side, left, center, and right side. And you should observe that the perceived order of features in the scene, by virtue of using a pinhole, will be inverted inside the pinhole camera. So camera A sees on the left position feature 1, on the center position feature 2, on the right position feature 3. I would like to know for which of the other cameras is it the case that feature 3 will appear in the leftmost position. So the leftmost position is L over here, L over here, L over here, assuming the optical centers shown over here. Please check any or all of the following: camera B, camera C, camera D, or none of them. And the answer is camera B and camera C. To C, we notice that the rightmost perceived feature in camera A's plane is called 3. So that's clearly the feature over here. This feature over here will come on left in camera B. It also comes in left in camera C, but it won't come in left. It actually comes in right in camera D. So the answer is B and C, but not D. My final question is a simplified self-driving car question that is usually solved using dynamic programming. But I have to warn you, the state space shown here isn't the full state space. The orientation isn't really made explicit in the state space. But suppose you have a road environment that has a straight street over here. You can turn left, go straight, or turn right over here. And similarly, you can turn left or right over here. And we assume that moving from one grid to cell to the next has a cost of 1, turning left has a cost of 14, and turning right has a cost of 1 as well. Let's assume the robot, when it turns, stays in the same grid cell, but it only can turn once. After it turned, it has to actually move. So it's impossible, for example, to turn right 3 times just to avoid the cost of a left turn. I would like to know what is the minimum total cost of going from the start location over here to location A. I realize there's many ways to get there. I'd like to know the minimum. So what's the minimum cost to get to A? Irrespective of what orientation you assume at A, I don't really care. The same from the start location to B and from the start location to C. Please enter your best guesses on the right side. And the answers are 10, 19, and 23. Let's look at A. We have to move 9 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9. And over here we have to turn right, which costs us 1. So the total is going to be 10. For B, there's 2 ways to get there. We can go straight and left, which will be 6 steps, but we're going to pay a cost of 14 for a total of 20. It turns out to be cheaper to take the loop over here and do 3 right turns, which is a total of 16 steps, and we have 3 right turns, which gives us 19. For C, I told you there's multiple ways to get there. We can go straight, turn left over here, straight, turn left over here and go around here, which looks inferior. Or do the right turn trick again, but now this time do 5 right turns to get to C. When you work it out, you find that going straight and turning left is the cheapest. These are 9 steps, and we pay the cost of a left turn, which is 14, adds up to 23. To answer this question, the very first thing we observe is that each statement implies itself. So we will draw every element on the Mann diagonal as true. We also observe that not pink implies green is the same as pink or green. If you do the truth table, you'll find that this is true either if green is true, which will be the case for B as well, or if pink is true, in which case the precondition to this implied will be false, and therefore the entire statement is true. So we can find out that B is exactly the same as D. With that in mind, we answer the question for A to C first. Pink clearly implies that pink or green is true. It doesn't imply that pink and green is true, so C is not open. But because B is equivalent to D, we also check over here. Pink or green doesn't imply pink, because green might be true. And doesn't imply pink and green, because green might be false. But it does imply D, because D is exactly the same as B. Pink and green implies pink. It also implies pink or green. And since B is the same as D, it implies D. And finally, for this one over here, we just copy over B. So we get this guy and this guy over here.